So we are essential
Okay.
here for the fourth talk from Professor Dasgupta. I request him
Yeah,
to
I will
please
start.
start.
Okay, so before we start the formal part of the presentation again, at least comments from where I left off, I thought it might be a good idea to show you at least one example of a representation which has direct physical significance, that is, would be useful for a physical problem. The only reason I'm doing this is simply because I showed you a lot of examples of representations in the afternoon session, but they look sort of like abstract things with, and it was a bit difficult to see what exactly the connection with physics is. So what I will do is I will just start this. Okay, I have to start my presentation, of course. So let's present my screen. And what I will do is show you at least one example of which is relevant for a problem which I will try to develop in the next few lectures that I have, that is molecular vibrations. I will talk about how group theory is used there, but I will do it in pieces. That is, today I'm going to right now talk about what kind of representation does the problem of molecular vibration give us. So let's see. Let's just, for the sake of simplicity, let's take a molecule which is very, very simple. Let's say it's a square molecule which is confined to move in 2 dimensions. It can move in various complicated ways. Say it can stretch, turn, do whatever it can. But we want to be able to figure out what we can say about its possible modes of vibration from the fact that there are certain symmetries of the molecule. So basically, what we are saying is this. We have a square molecule at the four corners of this red square, which I drew here.
Professor Dasgupta? Hello? Professor Dasgupta?
He seems to have left the meeting. Means there's some internet problem, I think.
I guess so. So maybe we wait for some time. He will be joining back.
So, any news about Ananda Dasgupta?
Nothing so far. I was trying to get him over phone. He is not reachable. Let us see how it's going.
No, if you have his WhatsApp number, maybe he has lost his internet connection or something like that. I don't know.
Okay, I just realized that for quite some time I have been cut off, or maybe for some time I've been cut off. Can anybody tell me how long?
So you are back. I was trying to get you over phone.
Yeah. I just realized that nobody was responding to a question I had asked. And usually it's not this much of a dead silence that I get. So, okay, so did anybody get to say anything? Or I don't know how long I've been.
So it's fine. You are back. No, actually, that you started.
Okay, now am I cut off again, or are you?
No, you are not cut off at all.
No, you are audible now, but
Yeah, presentation.
you were cut off almost for 6-7 minutes. 6-7 minutes you were cut off.
And people are still here. That's great.
Yeah. We thought that you have lost your network connection.
Yeah, I did. I didn't somehow. That's the problem. Somehow this is getting my browser crashed, which I didn't realize because I'm not looking at my browser now because I'm on the full screen mode.
Okay, so you just started by telling that you give an example, which is like has physical significance. Yeah,
relevance. Okay, you didn't get to see any of the example that I actually kept on speaking about. Okay, fine. So let me just repeat that. Okay, that is precisely why I gave you my phone number, because if I'm disconnected, you will not be able to call me back, tell me that over the connection. Okay, anyway, let's see. Somebody is saying I'm not audible. Am I not audible? Or is that a late response?
No, it's audible to me. I don't know about everyone else.
No, I think it was a late response from somebody. Or somebody, he had typed it earlier and maybe, yeah. Okay. Fine. So now it's okay apparently. So let's start presenting again. Let's just hope it stays stable. Yeah, it is. I'm actually trying a new browser, and that's maybe the reason why I had this problem. Okay. So let's. So I will talk about the direct sum representation, and finally talk about what reducible and irreducible representations really mean, because I've been referring to these terms several times before. But before that, as I said, as I promised, let's take a look at a physical situation. So the physical situation is something like this. Okay, maybe I will just get rid of all this extra stuff that I've written. Okay, so what we tried to describe was the problem that we are talking about is essentially the problem of vibration of a square molecule. So we have a fictitious molecule which is in the shape of a square, this red square here. There are 4 atoms in the 4 corners, and this molecule can vibrate in many different manners. And for the timing, we keep things simple. We are going to say it can only vibrate in 2 dimensions. So basically, each one of the atoms can move in 2 dimensions. And strictly speaking, the mathematical structure here is one. If I wanted to be very pompous, I would have said there's a vector bundle here, there's a vector bundle of over a 4-point manifold. What that means is basically this: there are 4 vectors which describe the motion of the 4 atoms, but each of the vectors are tied down to one corner each. So, of course, if you were to replace the vector here by a vector here, that would not talk about the same displacement, right? This would be a different displacement. So, the vectors here refer to the displacement of this atom, vectors here refer to the displacement of this atom, and so on. So, how do we describe this mathematically? Although a vector bundle is a rather pompous and difficult sounding thing, what we can easily say is this essentially is like an 8-dimensional vector space, right? So we can describe the motion, but just by describing the describing what happens to each of the atoms, and to describe each atom you need its position on a 2-dimensional vector space. Okay. So for example, this vector is the displacement of this atom, which will be of the form x1 e1 plus x2 e2. This vector will describe this atom, which will be of the form x3 e3 plus x4 e4, where e1, e2, e3, e4, these 8 basis vectors are simply vectors we have chosen for ourselves. Okay, these are our basis vectors. Now, these are not the best possible choice for the basis vectors for the problem. In fact, group theory, when used properly, will indicate that there are other choices which will ultimately make the problem easier to handle. But since we have not learned that much group theory here, we are just going by the simplest possible choice that presents itself. Just take Cartesian vectors e1, e2, e3, e4 at each corner. Okay, so this is how we are describing the problem. And the issue is that because the system is symmetric, this is a square, right? Remember, a square has 8 symmetry operations if you confine it to 2 dimensions. There are 4 reflections about the 2 medial bisector lines and 2 diagonals. These are the blue dashed lines I have drawn on the square. In addition, there are 4 rotations: the 0 degree, 90 degree, 180 degree, 270 degree. So we have 4 rotations, 4 reflections. These are the symmetries of the square. And the basic point I'm trying to make is the motion ultimately may end up looking very complicated, basically because the force law, the forces which atoms exert among each other may be very complicated. But they all have to be symmetric under these 8 symmetry operations. Because if you do a symmetry operation, you cannot distinguish the original square from the symmetry transformed one. So it would also happen that if, say, I have a displacement situation like this, where these are the way the 4 atoms are moving at a given instant, and of course, that's a time-dependent thing, so they will keep on changing with time. But if I were to reflect it, say, in this line, carry out the reflection A, which is a symmetry, then what will happen is I will get a new reflection, set of displacements, which will again evolve in time on their own. If I were to make a film of what the atoms are doing, but the new reflected version will be an equally good form of motion, equally valid form of motion as the original one was. And this is the basic hint which we are going to use to develop the theory of molecular vibrations over the next 2 lectures. But right now, what I want to show you is just this. Forget about the molecular vibrations and all that. We have an 8-dimensional vector space here, right? Spanned by the 8 vectors E1, E2, all the way up to E8. And because we have an 8-dimensional vector space and we have an action of the symmetry group, all the symmetry group elements on this 8-dimensional vector space, I should be able to find out 8-dimensional representations or 8 by 8 matrices which represent this particular symmetry group for us. So I'm just going to illustrate one of them, and that one is going to be this. What happens to these 8 basis vectors when you reflect along this line which I have marked A? Of course, what happens is E1, first of all, what happens to this atom? When I reflect along this line, this atom no longer stays here, it goes here, right? So E1, which is parallel to the plane of reflection, stays parallel, but comes here. So E1, this E1 becomes E1 prime. Is this clear to everybody? So under the action of A, E1 goes to E1 prime, but E1 prime is actually what? E1 prime is actually E7, right? This vector. So can anybody tell me what happens to E2, which is this vector? E2 of course becomes E2 prime, and that's already drawn on this reflected square. But what is E2 prime? E2 prime is?
Minus E8.
Minus E8, right. Right, minus E8. And by proceeding this way, you can easily write down what happens to each one of the basis vectors. And because once you have written that down, you can easily write down the matrix. For example, the 8 by 8 matrix that I will get representing A here will of course have 8 rows and 8 columns. And the first column is represented by the expansion of E1 prime, which is now 6 zeros, because there's no E1, E2, E3 all the way up to E6. A single 1 at the 7th position and then a 0, right? That's the first column. The second column will be 7 zeros followed by a minus 1. Just this minus E8. Is it okay? And this way, of course, I've just written down 2 columns of this 8 by 8 matrix. But by proceeding this way, you should be able to write down all the 8 columns. And you should be able to easily write down the 8 by 8 representation for DA. But that's just DA. It's equally easy to write down the matrices for DB, DC, DD, and all that. It's pretty straightforward. So I will not bother describing all of these to you. I just have one question. Can anybody tell me what is the character of this matrix? That is, remember the character is just a trace of the representation matrix. Can anybody tell me what that is? And I'm asking you this despite the fact that I have not told you what all the 8 columns are. You should still be able to tell me what is the character. Just by a simple argument. So this was a question which I asked and I had no response. So I just, yeah, it would be?
8.
8.
Trace should be 8.
8. Chi of A. You mean the trace of this matrix, right?
Yes, sir.
8. Can you argue that? Why should it be 8?
Because they are all independent and initially the matrix will be 1 0 0 0 1 0 0.
No, this is the matrix.
0, 0.
I have just written down 2 columns of the matrix for you. I have not written down the other 6. Right? So this.
Yeah, upon transformation, it should not.
So you mean if you transform it, it will become the identity matrix? I don't see why.
Upon diagonalization. Upon diagonalization.
Upon diagonalization, it will become the identity matrix. Why do you say that? Is there any? Upon diagonalization, it will become a diagonal matrix. But will the diagonal matrix necessarily become the identity matrix? I don't see why. If it became the identity matrix, by the way, the only matrix on which you can do a similarity transformation and get the identity happens to be the identity matrix. Right?
Yes, sir.
So this matrix definitely will not give you the identity matrix upon diagonalization.
Yeah. It is not.
Okay, what is the trace? The trace is basically the sum of all the diagonal elements. So all you have to do is look for in the transformed E1, how much E1 is there? In the transformed E2, how much E2 is there? And so on, right? Okay. But you can see in the transformed E1, there can be no E1. Why?
Yes, sir.
Why can't there be any E1? Well, you can say that E1 is actually becoming E7, so there is no E1. That's true. But it's easy to see that there can't be any. Which is? Because this atom, under reflection, has gone to a different atom, right? So any displacement of this atom will, under reflection, become a displacement of this atom. So anything which involves E1, E2 will become something involving E7, E8. I don't care what it will be right now. All I care is that there is no E1 in it, right? Can't be, because this atom does not stay here when you reflect. So the trace, this will not, E1 or E2 will not contribute anything. And notice that all the 4 atoms actually switch positions when you reflect along this line, right? Is that okay? This one goes here. This one goes, these two swap among themselves. So there is no way you can have a non-zero element because all the diagonal elements have to vanish. Quickly, what is chi B now? B is this reflection. Notice that I'm asking you this without asking you to calculate the matrix. What should chi B be?
It should also be 0.
It should also be 0 for exactly the same reason. All the atoms move. Well, let's stop talking about the reflections now. Let's talk about the rotations. A 90-degree rotation. What happens under a 90-degree rotation? This atom goes here, this one goes here, this one goes here, right? So once again, all the atoms are moving from their position. So whatever be the matrix, the diagonal elements have to be with 0, and that means all the rotations, which were ABCD were the reflections, EFGH were the rotations, but FGH were the non-trivial ones. All of them must have a character of 0. Same argument. All the atoms are moving, so they can't contribute anything to the trace. Well, this one. C, this reflection. Now that's slightly different, right? Here, this atom is moving, and so is this atom. These two atoms are swapping positions, but these two atoms are not, right? To find the character for chi C, all you have to do is look at this atom and this atom. Forget about the rest. But under C, can you tell me what happens to E1? Under reflection in this line, this atom stays here. But what happens to the vector E1?
We'll go to E2.
We'll go to E2. And what happens to E2?
We'll go to E1. So again, the trace will be.
So the diagonal, there is no E1 in E1 prime. There's no E2 in E2 prime. Same for E5, E6, right? E5 becomes E6. E6 becomes E5. Once again, no diagonal element. So what you can see is all the chi's are 0. Even for chi C and chi D. All of these are 0. All the characters, all for the group elements are 0, except for one group element, which is, there's one group element for which the character will never be 0. And what is that?
Identity.
Identity. And if you do the identity, what is the character?
8.
Yeah. So here chi E is 8, all the other chi's are 0. We already know one representation of this group which will have this same characters. Any idea which one that is? You might say we don't know any representation of this group because we only studied representations of the other group. The group which I was calling S3, although it was really the group of symmetries of the equilateral triangle. We have just seen this group, we have not constructed any of its representations, right? But we have already constructed general representations. And one general representation which every group has, just to remind you, is a regular representation. And that's an 8x8 representation, 8-dimensional representation, which has exactly the same characters as this. Okay? I'm not saying this is the regular representation. All I'm saying is that this has exactly the same characters as the regular representation of the group of symmetries of a square. That group also will have identity with character 8, everything else with character 0. Is it clear to everybody? You know, this is what, yeah, any questions? So this is what we are going to sort of come back to again when we apply the theory of characters and orthogonality of character vectors, etc., to find the reduction of this representation. This turns out to be a reducible representation Frankly, I should not even use that word right now because I've not defined for you what a reducible or an irreducible representation is. But then that is a shortcoming I'm going to correct right now. I'm now going to talk about how to build up representations from smaller ones, and as a direct consequence, I will be talking about reducible and irreducible representations. So first, the concept of direct sum of representations. We have already built up some examples of representations. We have found one-dimensional representations, which are just by numbers. We have one of them was a trivial representation. Every group element maps to 1. Another one was this determinant representation, where you take any representation whatsoever, find out determinant of the representative matrices, and just those will furnish a 1D representation. Now, in addition, we had also seen specific examples of 2D, 3D representations, especially for the group of symmetries of an equilateral triangle. And also a 6D representation for that, and an 8D representation of another group right now. Now, direct sum of representations essentially tells you that you can build up bigger representations starting from smaller ones. Suppose you have two representations, D1 and D2, and let they have dimensions N1 and N2. So D1 being a N1 dimensional matrix representation means that for every group element small g, you have a N1 by N1 matrix D1G, and another N2 by N2 matrix D2G, because D2 is also a representation. And of course, each of these obeys the standard rule that D1 G1 G2 has to be D1 G1 times D1 G2. D2 G1 G2 has to be D2 G1 times D2 G2, and so on. Okay, but now, given that you have these matrices, you can put them together into a bigger matrix, which has N1 plus N2 rows and N1 plus N2 columns. How do you make this matrix? Well, you just take the D1 matrix, D1G matrix, N1 by 1, N1, put them up on the first N1 rows and N1 columns of up here. And you, at the lower N2 by N2 block is made out by D2G. You just place them there. And the rest of these you just replace by zeros. So that this particular matrix has a nice block structure. You have a square matrix sitting here, you have a square matrix sitting here, and these rectangular pieces here are just zeros. Okay? So this is a new, bigger matrix. It's rather trivially easy to see that all you have done is put two representations together in this way. But the claim is that this is also going to be a representation. And for that, in order to see that this is a representation, you need to know how to multiply matrices which are in the block form. Is there anybody who does not know how blocked matrices multiply? Or does everybody know how to multiply blocked matrices using the block structure? Nothing to do with group theory again, basic matrix theory. I'm going to assume that the silence means, okay, I hope that the silence doesn't mean that I've been disconnected again.
No, sir, you did.
Does it?
No, sir.
No, I'm still here. But everybody knows how blocked matrices work, right? So if that is the case, then the proof becomes very simple. You can easily multiply. So there's one DG for every group element. So you take DG1, DG2. DG1 and DG2 both are of this form. They are both block diagonal of this form. D1, G1 sitting here, D2, G2 sitting here. You say it's block diagonal and not diagonal because of course D1, G1 and D2, G2 are not diagonal matrices. But this is a block on the diagonal, this is another block on the diagonal. Off diagonal blocks are zero. And now when you multiply them, you essentially multiply this matrix by this one plus this matrix by this one. And you should carefully check that such matrix multiplications are valid matrix multiplications by the row by row column rule and add them together. So it's just like treating them as elements. So if there were two elements here, A, B and C, D, you would have done A times C plus B times D. You just do that with matrices. And if you do that, then immediately see that this diagonal will become D1, G1, D1, G2. This one will become D2, G1, D2, G2. And these will still be zero. So this is also of the same form. Not only that, D1, G1, D1, G2 is of course D1 of G1, G2, and D2, G1, D2, D2, G2 is D2 of G1, G2. So what we have is that if you multiply dg1 by dg2, you get d of g1, g2, if you follow the same rule, which means that this bigger n1 plus n2 by n1 plus n2 set of matrices actually is also as good a representation as the smaller ones. But you should realize that it's really saying nothing very new. It's just saying that you have smaller representations, you just put them together and you're getting a bigger representation. Okay. So is everybody clear about this? If there's a question about this, please ask now. Okay. Now the block diagonal form that you see here, that DG is a block here, up here, another block up here. Okay. This clearly shows that you have actually built up this big representation by using smaller representations and joining them together. Okay, so you take smaller representations, you join them together, and you have built a bigger one, and that's apparent from the block diagonal structure. However, this is a block diagonal structure. This looks like neat block diagonal, and by taking one look at this, you will say, okay, this is a representation built out of smaller representations. But that's not always obvious, because if you change your basis, the matrices will undergo similar transformations, and all these terms will get mixed up, and you will no longer see a nice block diagonal structure any longer. So, an important question is, when is a representation built out of smaller ones? Simply because smaller things are easier to understand. So if you can build up bigger representations out of smaller ones, and you know that they are built out of smaller ones, then you essentially understand the smaller things, you understand the whole thing. But the trouble is, if you actually deliberately go about and build a representation out of smaller blocks like this, you will see a neat block diagonal structure. But in a physical application or in a mathematical application, several times you will get a representation given to you, like the representation that we saw right now, right? The 8 by 8 matrices that we had. The point that I'm trying to make is this. It's not so obvious just by looking at that particular set of 8 by 8 matrices whether I should be able to block diagonalize them all. And now, this might seem a bit of a stretch to you, because you all know that you can diagonalize matrices. So what's so great about block diagonalizing? Can anybody tell me why is it that despite the fact that usually most matrices can be diagonalized, in fact these matrices can be diagonalized usually, but despite that I'm saying that block diagonalizing them all may be difficult. Block diagonalizing is actually less restrictive than diagonalizing. When I diagonalize, I have to get zeros everywhere away from the diagonal. When I do block diagonalization, I can actually just also have non-zero values off diagonal as long as they don't stray too far away from the diagonal, right? That seems like a less demanding task than exact diagonalization, which I can do to each of the matrices. So why am I saying that it's difficult to block diagonalize? Or difficult to see whether you can at all block diagonalize?
So is it because the dimensions of the blocks have to be the same across the for all G?
Exactly. The point is, it's really not so much the dimension. The point is, you have to find a single similarity transformation which will block diagonalize all of the matrices together. So you will have not one matrix to deal with, but many matrices, as many matrices as group elements, and each one of them have to be block diagonalized by a single similarity transformation. That means it may not be so easy to find such a thing. Okay. In fact, the whole job of group theory, at least not whole job, but one part of the major job of group theory is to make such a block diagonalization easy for you. Give you hints as to how to proceed so that this block diagonalization essentially becomes trivial. More importantly, being able to tell you whether you can block diagonalize at all or not. But this is where this reducibility and irreducibility comes in. I've been using these terms often, but now I'm formally defining them. A matrix representation is called reducible if all the matrices, note the word all the matrices of the representation can be brought to the same block diagonal form by a single similarity transformation. Okay, this is very important. Single similarity transformation, all the matrices. This is what makes this not so easy a thing to do. Okay. Of course, that is why we need group theory. Otherwise, if this had been easy to do, we would not have to study any group theory at all. And when you say a matrix representation is irreducible, you say it is irreducible if no such similarity transformation exists. Now, that you should all realize, proving that something does not exist is way more difficult than proving that something exists. To prove something exists, you just show one example. That's it. Now, you can try many times and not be able to block diagonalize, but that doesn't show that you cannot block diagonalize, right? It just shows that whatever you have tried has not worked. So what we are going to now do is build up the machinery which will tell us, given a representation, whether it is reducible or irreducible. And it might come as a big surprise that ultimately all that you need to know are the characters. If you know the characters, that's enough. You don't even need to know the entire matrices, at least to find out whether they're reducible or irreducible. And even more, some more information from there. Okay. But let me just quickly tell you what this means at the linear algebra level, not at the linear representation level, not just at the matrix level. So we were talking of direct sum of matrix representations. Now we are talking of direct sum of operator representations, which are very similar. Here you have two abstract vector spaces, V1 and V2. And we can form a direct sum vector space, V1 plus V2. I don't know how many of you know about this, that you can form direct sums of vector spaces. The basic idea is simple. What is an element of V1 plus V2 is just a pair of vectors, one taken from V1, the other taken from V2. And how do you combine them? Of course, if you have a vector space, you have to tell me how to combine the vectors, how to linearly combine them. The rule is simple. You multiply V1, V2 by a scalar alpha and V1 prime, V2 prime by another scalar alpha prime and combine them together. The rule simply is V1, the first vector combines with the first vector here, the second vector combines with the second vector here, which essentially means each vector space does its own thing. So if you remember what we said about the direct product of groups, this is very similar. The direct sum of vector spaces is just a vector can be written down which is a sum of two vectors, which has two vectors, one in one space, one in the other. But when you combine them together, each piece essentially behaves like it's on its own. Okay? And if L1 and L2 are operator representations of a group G on V1 and V2, then the direct sum representation L1 plus L2, what does it do? It essentially says, okay, LG goes and acts on a vector V, but a vector V is one part which is from V1, another part is from V2. And what does LG do? Well, L1G acts on all vectors of V1. So L1G will go and act on V1. L2G will go and act on V2, will give you two vectors, and you just put them together in a pair. And this is your entire LGV. So that's what direct sum operator representation means. And you should be able to figure out very easily that if you have a direct sum vector space and you choose as a basis, what possible choice of basis can you make? Well, if you have a basis for capital V1, so E1, 1, E1, 2, E1 up to E1, N1, that's the N1 basis vectors which span capital V1, and you have some vectors which span capital V2, then it's very easy to see that these vectors, which are E1, 1 with 0 for the second basis, and 0 for the first piece, and EJ1, EJ2, E2, 1, E2, E2, 2, E2, 3, etc., E2, N2 for the second basis vector space. These together form a basis for V1 plus V2. That's rather easy to see because, okay, let me just show you what I mean here. So if I want an arbitrary vector from V1 plus V2, that's a single vector here, comma, another vector here. So what is this vector? This vector is, say, alpha 1, V11, E11, sorry. Okay. This is, let me just do this in steps. Any element of this, so any V which belongs to this is of this form. A vector V1, which is from here, another vector V2, which is from here. But any vector V1 can be written down as a combination of E11, so say, let's say C11 E11 plus C12 E12 and so on. Exactly N1 of those. That will give me the first vector, and then I will write down the second vector, which has E21 times a constant, let's call that C21, plus E22 times a constant, let's call that C22, and so on. Again, N2 of those, right? But this is really simply C11 times E11 here and 0 here, plus C12 times E12 here, 0 for the, this 0 meaning this entire piece, the second piece is 0. And if you want to make out the whole set, you will also need terms like C21 with 0. C21 E12 is one piece which has nothing coming from here, but E21 here and so on. So basically what I'm saying is you can write down any vector V here as a linear combination of these vectors, and they form a basis for your direct sum space. So if you use this basis, it is very easy to check. I'm not going to go into the details right now, but it's very easy to check that if you use these basis vectors and form the matrix for this L1 plus L2 representation, what you will get is exactly the block diagonal form that we were talking about. What is the difficulty? I've just said that finding out the block diagonal form may be difficult. What is the difficulty? The difficulty simply is that if you just have any such vector space, it's not so obvious that it was built out of these small pieces, on one of which L1 G acted, on the other one L2 G acted, because your basis vectors may be different. You may have chosen other basis vectors which mix up the two spaces, and then you end up with a complicated looking set of matrices. For example, a while ago we actually found out 3 by 3 matrices, right? Let me just go back a bit. Yeah, these were the 3 by 3 matrices we were talking about. Do they look block diagonal to you? Again, am I still here?
No, so they're not block. They're not
block diagonal right now, of course, right? This one is diagonal, of course. So is this one, but these are not block diagonal at all. You don't see any zeros, in fact. Now, it so happens that this actually can be. This is not block diagonal simply because we are using F1, F2, and F3 as our basis vectors. But if we were clever and chose other basis vectors, in fact, if we chose F1 plus F2, F1 minus F2 and F3 as our basis vectors, I would see that this actually breaks up into a 2 by 2 block and a 1 by 1 block. Now I'm saying this result because I know this. I've already done the reduction later on. I'm just giving you the result. But the point is, if I use some natural basis that may or may not be the correct basis to use, which will show you the reduction. Okay? And once again, the point is, the job of group theory, at least group representation theory that we are talking about now, is to make this reduction sort of obvious, sort of something which is visible. Okay, so let's... the basic idea here is this, that if you have a reducible representation, then V1, then what happens is, just let's look at what happens for the general rule. This is what happens in general, right? V1, V2 gives you LGV, which is L1G acting on V1 and L2G acting on V2. But let's just say that I choose a subset of these vectors, which are arbitrary vectors from V1 and zero vector here, always. Okay. So if I take this subset, which is also a subspace of the direct product space, which is essentially the same space as V1. So I've just taken a fixed vector V2, which is the null vector here, and taken just the V1, all vectors from V1. If I apply LGV on that, what will happen? I'll get L1G V1 and 0, right? L2G acting on V2, where V2 is a null vector, will of course give you 0, right? What that means is, if you just take a subspace in which the first piece is an arbitrary vector, but the second piece is always 0, that subspace stays invariant under the action of LG. I don't mean that the vectors don't change. All I mean is that if you start from that subspace and apply all the LGs, you stay within that subspace. Okay? Is that clear? This is a critical point. This is something which should be understood by everybody. The fact that you have a reducible representation shows that there is a subspace, a smaller subspace, which is invariant under all the LGs. What that means is the vectors in that subspace only mix among themselves under the action of all the LGs. They don't mix with the other vectors, and which is why if you were to choose your basis just correctly, you will be able to see a block diagonal structure. Just those matrices mixing among themselves, those basis vectors mixing among themselves, and other basis vectors mixing among themselves. Is there a confusion about this? This is an important point. So,
sir, what is mean by mixing among themselves?
So, okay, let me just go back to my scratch pad and let's try this. Let's just think of a situation like this. E1 goes to E1 plus E2. E2 goes to E1 minus E2, and E3 goes to E3. Let's say this is a particular change of transformation which I'm carrying out. Now this is just one transformation. Now there will be as many such transformations as there are group elements. But at least for this one, you can see one thing, that E3 only mixes with itself, right? And E1, E2 actually mixes among themselves. There's no E3 here, right? When you transform E1, E2, you're not getting an E3 piece. You transform E2, you're not getting an E3 piece. But E1, E2 do get mixed up. Okay? Now, if it so happens that the other matrix, other transformations, this is for one group element, say G1. So LG1 does this to E1, E2, E3. Say LG2 does this. Takes E1, moves it over to say minus E1, minus 2E2. E2 moves it over to E3 becomes 5E3. Can again see that under LG2 also, E3 only, well, mixes with its own self is hardly mixing. It just comes back. But if you have two vectors, E1, E2, they keep on mixing among themselves. At least mixing here is just they linearly combine among themselves. But they don't mix with E3. There is no E3 here. Okay. Similarly, E3 does not mix with E1, E2. What if this were to recur for all the LGs, then what we will say is, instead of just E1, E2, take any vector of the form V1, E1 plus V2, E2. If you apply all the LGs on that, what will you get? You will get a combination of E1, E2, right?
Yes, sir.
That would mean that the two-dimensional vector space spanned by E1, E2 would be invariant or would essentially be, it's called invariant. It essentially, the terminology simply means that if you start with a vector in this 2D subspace, you stay in that 2D subspace. You're not going out of it. Although your space is three-dimensional, when you start with this, with any vector in the 2D subspace here, you stay within that 2D subspace. Whereas if you start with vectors in the 1D subspace, which is spanned by E3, start with any vector which is multiple of E3, and you apply LG1, LG2, LG3, all of them, it will get a multiple of E3 back. So the one-dimensional subspace spanned by E3 is also invariant under this. And the moment you have invariant subspaces, you end up with a block diagonal structure, provided you have chosen your basis correctly. Why do I say chosen your basis correctly? Because you could just as well have chosen, for example, instead of E2 and E3, E1, E2, E3, you could have chosen E1 plus E2, E1 plus E3 and E1 minus E3 as your basis vectors. And the moment you do that, you should be able to check very easily that now you can no longer directly see from the transformations that there is an invariant subspace. It's not so obvious. Here it's obvious that E1, E2 only mix with each other. E3 only mixes with itself. I'm just using mixes in a colloquial sense. It just means linearly combines. Okay. So you just wrote down these transformations using these basis vectors. That's pretty easy to do. Just try it. You will find that the matrices no longer look block diagonal at all. And so the invariant subspace is still there. It's not so obvious to see. Okay? Is this
Okay, sir. I got it.
Okay, fine. I just hope that I did not intimidate you into saying you got it. Because if somebody stresses the point long enough, it might sometimes seem like you should understand it anyway. But anyway, let's proceed and see. Okay, so let me just skip into these some basic details. But basically, an operator representation L on a vector space V is said to be reducible if there exists a subspace V prime of V which is invariant under the action of LG for all G. That is, if there is a subspace, a smaller subspace, non-trivial subspace, not the whole space, which is invariant under the action of LG. That is, apply LG for all the G's. So LG1, LG2, all of them apply on vectors in the subspace. You stay within the subspace. You don't go out. Then you have an invariant subspace. Okay. I will talk about the physical significance of this in the next class. In that case, you will see why invariant subspaces are so great. But for the time being, this is just a mathematical definition of it. Okay. Now, I will not go into the details. I've already said this, but maybe this complete reducibility, etc. Let's forget about that. There's another kind of way of building up big representations out of small. They are called direct product representations. And you have seen direct product representations very often. Can anybody tell me one example of where you have seen a direct product of a representation in quantum mechanics? Of course, you may not have used that nomenclature, so you may not know that you have been dealing with a direct product representation. But any idea of a direct product representation? Anybody?
Angular momentum.
Angular momentum, where is the direct product? Angular momentum is just a representation of rotation group. But yeah, in the theory of angular momentum, you have seen direct product representations. It's the addition of angular momentum. Yeah. The addition of angular momentum really is a theory of direct product of representations of the rotation group. I hope to have enough time to clarify that in the last lecture. That is the sixth one, which I have sort of forced out of the organizers. So I will talk about direct product representations later when I talk about angular momentum. So let's skip this part. Now comes the basic theorems or basic lemmas. They're called lemmas, not theorems. And these are the basic lemmas which help us to understand reducibility, irreducibility, and various other aspects of representation theory. They are basically theorems from linear algebra, not really theorems from group theory. And they're easier to state in linear algebra language than in group theory language. In fact, most group theory texts make them seem to be very complicated simply because they only state them in the context of group theory. But if you understand them in the context of linear algebra first and then talk about how they sort of show up in group theory, it's much easier to understand them. These are called Schur's lemmas or Schur's lemmas. I don't know how to pronounce the name. Isaiah Schur, who was Isaac Schur, perhaps, or Isaiah was its original Hebrew name, possibly. Anyway, these two things, there are two lemmas. These are Schur's lemma 1 and Schur's lemma 2. But before I go there, let me just ask you a question. What do you think is more important, a theorem or a lemma? Yes? You know that in mathematics you have theorems, lemmas and stuff like that. So what is more important? What do you think is more useful, a lemma or a theorem? Everybody knows what a lemma is, right?
No, sir.
No, okay, lemmas are things which you must have learned about long ago in geometry, perhaps. Lemmas are results which are used to prove theorems, some part results. So it might seem that theorems are more important, but frankly, when a lemma is important enough to give it a name, named lemmas, like Schur's lemma and so on, the reason why you give a lemma a name is because this lemma can be used to prove many theorems, not just one theorem. So in that sense, a lemma, especially a lemma important enough to have a name of its own, is actually more important than most theorems, because they are the building blocks out of which theorems are proven. So let's just state what those lemmas are, but for that we will need some definitions first. Now, first, let me just recapitulate that you may have an invariant subspace for the action of an operator. When an operator T acts on a vector space and you pick a vector from a subspace, the vector may or may not stay within that subspace when you apply T. But if it does, if it so happens that you have a subspace for which every element stays within that subspace on the action of T, you say that's an invariant subspace. That's the concept that we have been using so far. Now, no matter what operator you're dealing with, as long as you're dealing with a linear operator, and that's acting on a vector space V, there are two subspaces of V which are always invariant. One is, of course, the full space. The full space technically is also a subspace of V. And of course, if you pick any vector from V, apply T on it, you stay within V. That's trivial, right? So the full space V is always invariant. Okay? And another space which is always invariant is the space, the trivial linear vector space which you get just by taking the null vector and nothing else. That's a subset. Remember, a subspace of a vector space is a subset which is also a vector space in its own right. Okay? Right? The null vector alone is a subspace, right? Because what makes something a vector space? If you linearly combine its elements, you should stay within that set. So take the null vector, linearly combine it with the null vector, you stay at the null vector. So that's a subspace, the null vector alone. That's a subspace which every vector space has. It's a trivial subspace. And the other trivial subspace every vector space has, no matter what the structure is the full space. And these two subspaces are guaranteed to be invariant under the action of every linear operator, because if you take a null vector and apply a linear operator on it, you're bound to get the null vector in return, right? So these two invariant subspaces are always there. So you can never have a situation where you have an operator which does not have invariant subspaces. These two will always be there. But if you have a bunch of operators, T1, T2, T3, etc., such that the only subspaces which are invariant under the action of each one of them, T1, T2, T3, etc., are these trivial subspaces. The trivial subspaces will definitely be invariant under the action of each one of them. But if they are the only ones, then you say that the set of operators is an irreducible set of operators. Okay. This again has nothing to do with group theory. This is a linear algebra concept. Is this clear? You say a set of operators is irreducible if the only subspaces which are invariant under the action of all of them are the trivial ones. That is just the null vector and the whole vector. And why are they so important? They're important for us in group theory because if you have an irreducible representation in group theory, that means you don't have any invariant subspaces under the action of all the LGs. That really means LG, the set LG, which is LG1, LG2, LG3, LGN, all of the LGs together, they form an irreducible set of operators on that particular vector space. So irreducible representation essentially means that you have an irreducible set of operators. Now, the reason why I brought up this irreducible set of operators is that the lemmas are easy to state in terms of them. And what are the lemmas? Lemma 1 is simply this, that if you have two irreducible set of operators, Ti1 and Ti2, acting on two different vector spaces V1, V2. Okay, not necessarily two different vector spaces, but two vector spaces V1 and V2. Maybe same, maybe different, but they are two sets of irreducible operators. And you have map X, a linear map which goes from V1 to V2, which has this property, X. Remember, X is a map from V1 to V2. So what I can do is apply Ti1 first, and then apply X. So Ti1, of course, takes a vector in V1 to a vector in V1. Then you apply X, it goes to V2. So this combined thing on the left takes a vector from V1 in V1 to a vector in V2. On the other hand, I could do it in the other order. I could apply X first, and then apply Ti2. Okay? X takes you from V1 to V2, and Ti2 acts on V2. So this takes a vector in V1, ultimately to a vector in V2. It so happened that X actually obeys this, X Ti, whether you do X after doing Ti1 or you do X before doing Ti2, you get the same result every time for every one of the i's. Remember, i's here label an irreducible set of operators. So if you have such a relationship that X looks like X is commuting with Ti's, right? But they are not really commuting because the two operators Ti1 and Ti2 are not the same operators. Okay? Ti1 are operators which are acting on the space V1, Ti2 are operators which act on the space V2. So they don't have to be the same operators. Okay? So this is really not commutation. This is something called intertwining. Okay? And you will see when somebody talks about braid groups later, you will see more examples, more non-trivial examples of intertwining. But this is what intertwining means here. And basically, X intertwines between Ti1 and Ti2, the two sets of irreducible operators. If this happens, then a very useful result comes about. The useful result is either X is 0. Of course, if X is 0, the null operator, then this is trivial, right? Then no matter what Ti1 does, then you apply X, you're going to get 0. Or Ti2, no matter what Ti2 is, if X is 0, you get 0 vector in V2 and then Ti2 gives you 0. So if X is 0, then X is a null map, then the map which maps every vector in V1 to the null vector in V2, then of course this is trivial. But if X is not 0, then something rather special happens. The only non-zero map which can do this has to be such that its inverse must exist. If this happens, the inverse must exist. The converse is not true, by the way, before anybody asks. It's not true that every non-singular map, every map which has an inverse, will intertwine between Ti1 and Ti2. But what is true is if a map intertwines between Ti1 and Ti2 for each I, then it can either be only 0 or its inverse must exist. Okay? And lemma 2, yeah.
Hello.
Go ahead.
That is your X is some linear map actually. Yeah. It's an operator also.
Okay. Yeah, a linear operator and linear map, they're sort of interchangeable, but operator, usually you use the word operator when it's a map from a vector space to the same vector space. You usually don't use the term operator when it's between two different vector spaces. Okay.
Sir, are we also guaranteed that X is going to be unique? That
no.
intertwining map?
Not at all. All we are saying is, if you have an intertwining operator map like this, which intertwines between Ti1 and Ti2, so that the action of Ti1 first, then X, and X first, then Ti2 is the same for each of the i's, then this is the condition. Then if such an X, if for all such X's, there are just these two possibilities. Either X is 0 or X must be a map which has an inverse. I'm not saying anything more. That's lemma 1. Okay. I'm not saying X is unique at all, because it's not, right? X is 0 will definitely work, and there will be some non-singular X's for which this will work. And there are many non-singular X's for which this will work. X is not unique in any sense, but if X obeys this, then X has to be either 0 or inverse X's. That's all the lemma says. Okay?
Yes, sir.
So this is about, well, I would not really call X an operator all the time, because X typically is a map between two different, it is a linear map, but it's a linear map, maybe a linear map between two different vector spaces. Of course, if V1 and V2 are the same space, then X would be a map from V1 to V1, and then you would usually call X also an operator. Okay. The term operator is usually reserved for linear maps between a space and itself. Okay, in fact, lemma 2 deals with such a situation, that instead of having two vector spaces necessarily, by the way, just to clarify, in lemma 1, we are not saying that there are definitely two vector spaces, but there could be. V1 and V2 could be the same, they could also be different as far as lemma 1 is concerned. In lemma 2, you have only one vector space V, and you have an irreducible set of operators, T1, T2, T3, Tn, on that. And we have a operator now, a linear map from V to V, which actually commutes with all the X, all the Ti's. Okay. So here I have an X which commutes with all the Ti's. So an operator which commutes with all the operators in an irreducible set of operators. Can anybody tell me what an example of such an operator? An operator which commutes with all operators. Forget irreducible set. An operator which commutes with all operators.
Identity.
Yeah, but is that unique?
Proportional to identity.
Anything proportional to identity. So it's, even that is not unique, right? But actually lemma 2 says that you don't have to go so far as to claim that this X commutes with every operator. If X commutes with every member of an irreducible set of operators, then lemma 2 demands that X must be a multiple of the identity operator. So that puts a huge restriction on possible X's. It's not unique, but it has to be a multiple of the identity. Of course, you might say 0 will work. Of course, 0 will work, but 0 is also a multiple of the identity operator. It's just 0 times the identity operator, right? So this is what lemma 1 and lemma 2 says. If somebody is interested, I will discuss the proofs of these two lemmas later. But the proofs are actually rather simple. So if you know something about kernels and images of linear maps, the proofs are really rather trivial. But right now, let's skip to applications. Remember, these have been stated in terms of irreducible set of operators, but the real reason why we are interested in them is that as far as in group theory, if you have an irreducible representation, then all the LGs form an irreducible set of operators on that particular vector space. Okay, so we will now move on to applications of Schur's lemmas, skipping the proof, which actually is the next few slides. So we'll quickly, okay, let's look at one application, a very simple application. It says irreducible representations of an abelian group are all one-dimensional. That's the theorem. That something can easily prove by just applying Schur's lemmas. So I will not even give you the proof, simply because the proof is very simple, and if you have understood what Schur's lemma states, or you try to understand what I have said right now about Schur's lemma, you would be very easily able to show that you cannot have an irreducible representation, which is shortened to irrep. By the way, irreducible representation is a mouthful. It's very difficult for me to pronounce it. Somehow I cannot really pronounce irreducible representation very nicely. Irrep is much simpler. And irrep is a standard abbreviation. So I will call it an irrep. If L is an irrep of an abelian group, you can show it has to be one-dimensional. If it's more than one-dimensional, it has to be reducible. This is something which can easily prove just by using Scho's lemmas, the two lemmas that I stated. So just think about it. Okay, I will not tell you what the proof is because it will not be part of the rest of the talk, and B, because it's a very easy thing for you to think about yourself. Let me just do one thing. Let me move on to the next part of the presentation, which actually should have been my third lecture. Okay, the lecture. So this should have been the lecture I would have given if everything went according to plan, if my speed really had been correct, in the afternoon today. And I will just start this and we will have some discussions after that. The next big application of Scho's lemma, the real reason why it's so great and so important in group theory, is something called the Great Orthogonality Theorem. This is the original GOT, of course, way before the Game of Thrones came into the picture. And this is really great. That's why the name actually is very, very important. It's called great because it's one of the central results of group representation theory. And almost every other result in group representation theory comes out of the GOT. So these are just restatements of the Scho's lemmas, which I have here. Then we are going to use the Scho's lemmas to prove the Great Orthogonality Theorem. But let's state that first. In the Great Orthogonality Theorem, what we do is we will now focus on matrix representations. So let's say d alpha and d beta are two irreps. Just to remind you, what are irreps? Irreps are matrix representations which cannot be further put into smaller, simpler block diagonal forms by any similarity transformation. Okay. Remember, when I say block diagonal form, I mean all the matrices for all the d alpha g, all g's d alpha g should be in the same block diagonal form. If that is impossible to do, then you say it's an irrep. Okay. So let d alpha and d beta be two irreps, which are either. So what I'm doing is I'm just labeling the irreps of a group. We will soon see that at least for a finite group, the number of irreps is finite. In fact, it's pretty small in most cases. So it is for small groups. And we can label all of them. But of course, given a representation, you have infinitely many more representations just by changing the basis, right? These are all equivalent representations. So we will just not count them. So what we are doing is this alpha index here just labels my irreps. So I will have D1, D2, D3, and so on for all the irreps that I have. And I've decided that I will only count inequivalent irreps. What that means is, if two irreps are, if I've already counted, say, some irrep as D3, and I find another irrep which is actually equivalent to this, just something which comes from the original irrep by doing a change of basis, I will not count that as a new irrep. That will not be in my list. So this listing is being done using the index alpha, and d alpha and d beta are two irreps which are either identical. If alpha and beta are equal, then they're identical. If alpha and beta are different, then they are not only not identical, they are inequivalent. They cannot be equivalent. You will not list two equivalent irreps in the same listing. Okay, once you do that, then let's consider this matrix. Notice d alpha g is a small d alpha dimensional representation, and d beta g is a small d beta dimensional matrix. So what I'm doing here is I'm taking this matrix d alpha g, which is d alpha by small d alpha by small d alpha. This matrix d beta g inverse, which is small d beta by small d beta. Okay. Putting a matrix Z in between, which is an arbitrary d alpha by d beta matrix. Of course, that means that this whole thing, forget the sum for the timing, this whole thing becomes a d alpha by d beta matrix, right? This is d alpha by d alpha, this is d alpha by d beta, this is d beta by d beta. This matrix multiplication is well defined. It's a d alpha by d beta matrix. Clear? But I don't stop there. What I do next is that I have one such matrix for every group element G, right? For every group element G, I have a d alpha G, I have a d beta G inverse. So I form this combination for that G and then add up over all the group elements in capital G. Okay. This is a matrix I'm constructing, and I'm going to use this to prove the great orthogonality theorem. The statement of the great orthogonality theorem will come at the end of a sequence of arguments. But to get there, I'm just creating this particular matrix for us. Why am I creating a matrix of this form? It will be very clear soon. But everybody understands what the form of this matrix is, right? I hope there's no confusion about that. And of course, there are infinitely many possible such matrices because you have infinitely many possible, even with d alpha and d beta are fixed, even then Z can take infinitely many possible values. So there are infinitely many such possible matrices. I've just taken one arbitrary Z and formed this X. And the next step is, I will take this X and multiply it by d alpha G on the left and d beta G inverse on the right. That is, this is the X, right? Remember, this G is a specific group element. This is a sum over all G. And as in all cases, when you have a conflict between an index of summation and a specific index, you have to change the index of summation to something else. So that is why this X has been written down as a sum over G prime. Clear to everybody? This, of course, is nothing but this with G prime being used instead of G, and I've hit it with d alpha G on the left and d beta G inverse on the right. Again, this is a legitimate matrix multiplication because remember, X is a d alpha by d beta matrix. So I can multiply it from the left by a d alpha by d alpha matrix and from the right by a d beta by d beta matrix. Okay? But then comes the next step, which is sort of obvious. This sum over G prime runs over the entire group. This d alpha G is the same for every G prime. So I can just move the d alpha G inside, also move the d beta G inverse inside. So what do I get? I get d alpha G prime, Z, d beta G prime inverse, d beta G inverse, right? So just note, this is what I had. I've just moved this in. I've moved this in into the sum. And this is where having finite groups is handy because interchanging matrix multiplications with sums is fine as long as you're doing it for the finite sum. For infinite sum, you have to be much more careful. So if this were an infinite group, you will have to demand some additional properties like compactness, etc. for this to work. But for finite sums, this is just trivial. You're just moving the matrix multiplication first and doing the matrix multiplication first here and first here. And now, what is this? This is d alpha G prime. And what is this? This is d beta of G prime inverse G inverse. But what is G prime inverse G inverse? It is G prime's inverse, right? That's something I guess everybody knows, right? That when you invert, you get in the different order. So it breaks up like this. Oh, sorry, I got the wrong way. This is what you have. Now, compare this sum with this sum. Are they the same sum?
Yes, sir.
Why do you say they're the same sum?
Because G prime, it should be element of G.
Yeah, it's an element of G. But what guarantees
So
that?
For all G, the summation is over all G, right?
Right.
So, since
So
G
yeah,
prime,
there's a theorem that we talked about in the very first class, which is the theorem that you should quote here, so that one name should tell you what the answer is. Although, I guess you are giving the right argument, but what we are really seeing here is an example of the rearrangement theorem, right? Because notice that here what we have, the sum is over G, where G runs over the entire group. Here the sum is over G prime, where G prime runs over the entire group. But when G prime runs over the entire group, so does G prime. It's just one column of the multiplication table, and that's just a rearrangement. So you just get the same terms in a different order, perhaps. but you get the same terms, right? So whatever terms go into this sum are the same as the terms which go into this sum. Now this is an argument which is used over and over again in representation theory, so you should get used to it. But this shows that this thing is actually x. And that is precisely why I did a summation over all g. Remember, if I did not have the sum over g, then this doing d alpha g, d beta g inverse from this side would simply have given me d alpha gg prime, d beta gg prime inverse. So some other term. But when I sum over all g, I end up summing up over the same terms, maybe in a different order, but I must get the same result. So this is what is called, this is what we have. But what does this mean? It simply means that d alpha gx must be equal to x d beta g, right? So what can you say about this x? What does this say about the x in the language that we had used for Schuss lemmas a while ago? Yes?
Intertwining.
It intertwines between the two sets of irreducible operators, right? D alpha g are irreducible operators on their vector space, d beta g. They are matrix versions, but they are matrix versions of irreducible operators, and d beta g are irreducible operators on their vector space. And x intertwines between them. So what does lemma 1 tell you?
If x equal to 0, then d alpha and d beta are inequivalent.
Or rather, you would have to say there are two possibilities. Either x is 0,
or not equal to 0.
Or the inverse exists. It's not just not equal to 0.
An inverse exists. Then
if the inverse exists, then d alpha and d beta would end up becoming equivalent.
Equivalent.
Because then d beta would be x inverse d alpha gx, right? But since we have made up the law at the very beginning, we have said that we will not count equivalent representations, then x inverse cannot exist. So either x is 0, or what is the other possibility? If alpha and beta are different, we are talking of inequivalent representations, then x cannot be invertible, x must be 0. Okay? But if alpha and beta are the same, then basically what you're saying is x is a matrix which commutes with all the elements of an irreducible set of matrices. So what does it tell you about x? Now comes lemma 2. If alpha is not equal to beta, then d alpha and d beta are inequivalent representations, so x inverse cannot exist because that would have contradicted the inequivalence of the two representations. Then x must be 0. If alpha is equal to beta, what do you get?
X is identity.
Well, not the identity, but a multiple of the identity.
Multiplication.
Right? So, this is your final result. Not the final result, but this is nearly the final result. This matrix d alpha g z d beta g inverse is delta alpha beta, because if alpha and beta are different, it's going to be 0, times the identity, times a constant c. Okay, which identity? Is it a d alpha by d alpha identity matrix or a d beta by d beta identity matrix? The answer is it doesn't matter, because if alpha and beta are different, then there's 0 anyway. I don't care. Then the whole right hand side is 0. If alpha and beta are the same, then the right hand side comes into play, and then I is just the d alpha by d alpha or d beta by d beta identity matrix. They're the same anyway. And c, of course, is a constant which will depend on what z you have chosen. Okay. So notice that I'm saying something rather strict here. Choose whatever z you want. This combination is going to be a multiple of the identity times delta alpha beta. So that's really a huge restriction. So I will just end up by telling you what this T is, and that's actually pretty easy. Any ideas how to, okay, by the way, everybody can spot that there's a big typo here. Depends is spelled wrong. But anyway, can anybody tell me how to find out the constancy? Any ideas? Any ideas about how to find the constancy? Okay, let me just give you a hint. This is a similarity transformation, right? But this whole thing is there's a sum after doing a similarity transformation. So you need something which talks nicely with similarity transformations and also nicely with addition. Can you tell me, you all know about matrices, right? What things say the same when you do a similarity transformation?
Trace.
And also determinant, right?
Yeah.
But determinant is not a nice idea because there are sum of matrices. And determinant of a sum is not a simple thing at all. But a sum of a trace is simple. It's just a trace of a sum is sum of a trace, right? So if you take the trace of both sides, what will you get? Well, first of all, to find C, you set alpha equal to beta, because if alpha is not equal to beta, anyway, this will go away. That's what I meant when I said this is similarity transformation. Otherwise, it wouldn't be. If alpha and beta were different, this would not be a similarity transformation. But we are saying alpha and beta are the same. So now you have a constant times identity. If I take the trace now, what do I get? What is the trace of d alpha g z d alpha g inverse?
We have to use the cyclicity property of trace.
Yeah, and then?
Z.
The trace of the...
It will trace of z, right? The trace of d alpha g z d alpha g inverse is just the trace of z. End of story. But what is the trace of the left hand side? Tell me that. It's pretty easy. Just tell me that.
Alpha Z?
Alpha z. What is alpha?
Dimension?
No. No. How many terms do you have on the left hand side?
The number of group
Number of group elements, and each one of them give you trace of z. So you have number of elements of the
number
group
of
mod
elements
g
of the group.
times trace of z. That's the left hand side. What's the right hand side? Right hand side is a trace of a matrix which is constant times the identity matrix. So what is that trace?
C alpha.
That's where the d alpha comes in. That's C times d alpha. Right? The trace of a d alpha by a d alpha identity matrix, that's just d alpha. So what is C? C is just number of elements in the group G times trace of Z divided by d alpha. So this is the orthogonality theorem written down in full for an arbitrary matrix Z, d alpha G Z d beta G inverse summed over all group elements is simply mod G by d alpha, that's just a factor that we just calculated, times the trace of Z, times delta alpha beta, times the identity. Okay. This may not look very impressive, but let me just make it a bit more impressive for you. This is a matrix relation, right? So I can take its elements. So what I can do is I can just take this matrix rule, law that I have, and take the ijth element of both sides. So what will the right hand side be? All these things sitting here, mod G, d alpha, d alpha, trace Z, delta alpha, beta, they are just numbers. So you just get the ijth element of identity, which is just delta ij. What do you get on the left hand side? Get dik alpha G, zkl, d beta, lj G inverse, right? That's how you sum up. Now, let's make a very specific choice of zkl. Zkl is completely arbitrary, right? But I can choose zkl in a very special way, which will make this look very simple, or rather, lot simpler than it looks right now. Let's choose the matrix zkl in such a way that only one element of zkl is non-zero. Okay, let's choose a matrix such that only one element is 1, every other element is 0. If you recollect your matrix theory, you would realize that what we are talking about are independent matrices which which can be put together to build up any ZKL. Just say one element, one matrix for which the 1, 1 element is 0, another one for which the 1, 2 element is 1, 1 element is 1, everything else is 0. Another for which the 1, 2 element is 1, everything else is 0, and so on. So let's make the specific choice that that ZKL is of this form. Delta K I prime, delta L J prime. That means that only when K is equal to I prime and L equals J prime. So the I primeth row, J primeth column is 1, everything else is 0. But if you use that, you can simplify this expression substantially. Can you see that? Remember, you have a sum over K and a sum over L on this side, right? You have a sum over K and a sum over L. And if ZKL has delta K I prime and delta L J prime, you should all know the summation is very simple if you have delta symbols, right? What happens? There is sum over K and you have a delta K I prime. When you sum over K, what's the result? All the K's in the rest of the expression, of course, delta K I prime you no longer have after the summation. But in the rest of the expression, whatever happens is all the K's get replaced by I prime, right? And all the L's get replaced by J prime. So that's what happens to the left hand side. On the right hand side, you need the face of Z. Can anybody tell me what is the face of Z? This is a matrix for which, by the way, once again, you might say Z could be rectangular, d alpha by d beta. Then what's the meaning of the face? Remember that that term only comes in when alpha is equal to beta. So that's a square matrix. Remember, Z has only one non-zero element, a 1 in the I primeth row, J primeth column. What is the trace of such a matrix? A matrix which has 1 in I primeth row, J primeth column, and 0 everywhere else. What's this trace?
DA.
Sorry, I couldn't get you.
I prime, J prime.
It's delta I prime, J prime, right? If I prime and J prime are different, then it's 0 because that only one non-zero element is sitting outside the diagonal. If I prime is equal to J prime, then the non-zero element is sitting on the diagonal and you get a trace of 1. Using this, you'll simply get this rather wonderful result, which will be the source of all the results that we will talk about tomorrow. Just to emphasize how wonderful this result is, let me point out that here there's only one sum on the left. The sum is over the group elements G, right? But what do you have here? You have I, which can take any one of the d alpha values, I prime, which can take any one of the d alpha values, J prime and J can take any one of the d beta values. So these are really d alpha squared times d beta squared equations. One for each possible value of I prime, J prime. And what this is telling you is that this combination, most of the time is going to be 0 when either alpha is not equal to beta or I is not equal to J or I prime is not equal to J prime. And only when I is equal to I prime and I is equal to J and I prime is equal to J prime. Okay. And alpha is equal to beta, we will get a non-zero value and the non-zero value will be mod G by d alpha. So notice that we wrote down a lot of matrices before for representations. These are about these representation matrices. But what we have found is that if the representation matrices represent irreducible representations, these are only for irreps, then this huge amount of restriction occurs on them. The group elements cannot be just anything. These are elements of the matrix that we are talking about, and the elements of the matrix are strongly constrained by this innocuous looking or complicated looking expression, whatever you have it. But this is really a huge number of restrictions which will severely constrain irreducible representations. So ultimately it's rather difficult for a representation to be irreducible, which is great for us because that helps us to figure out which representations are irreducible, which ones are not, with relatively less effort. So we are going to pick up from this the next day. I know that I've already overshot by 15 minutes, but I lost 6 or 7 minutes at the beginning, so I'm just using that as an excuse. But are there any questions at this stage? Just this, note down this one expression. This is the one which is going to be useful for all that I'm going to do tomorrow. And just to give you a hint what this can do, this can tell you whether a representation, arbitrary representation that you have picked out is reducible. It can tell you whether, if it is reducible, it can tell you how many times different adepts occur in it, and lots of other things besides. It can also tell you how to pick out your basis in such a way that the invariant surfaces are displayed automatically. So everything that we are going to do tomorrow falls from this. So just before I wrap up, any questions? Yeah.
Sir, here the delta alpha beta on the right hand side, the expression implies that implies that for any non-zero value of this expression, alpha and my d alpha and d beta are equivalent, right?
No. What it implies is that if you take, remember in this whole set of adepts that I've written down, every adept is of course equivalent to itself, right?
Yes, sir.
So I never meant that you cannot have equivalent adepts. I said they're either identical or inequivalent, right? So if alpha is equal to beta, that means we are talking about the same adept. So d alpha and d beta are the same. They're not equivalent adepts, they're the same adept.
Okay. So the reason I was asking was, if we have that, then why do we not just drop the alpha and beta indices and simplify that?
Because if this also tells you what happens when you have two different adepts. You have different adepts, then it tells you that the sum is 0. And that's being 0 is important. By the way, this is called the orthogonality theorem, right? The name orthogonality should tell you that it's really the 0 which is more important than the non-zero value, right? What does orthogonal, when do you use the word or term orthogonal? You say two vectors are orthogonal. When?
And there is some inner product that is 0.
When the inner product vanishes, or in class 12 language when the dot product is 0, right? So it essentially says that there is an orthogonality between different adepts. It also tells you what is the normalization if you use the same adept. But the orthogonality between different adepts is actually critically important.
Okay.
So alpha is not equal to beta means the right hand side is 0. That doesn't make it unimportant. That's actually a very important restriction. All this will tell you several things, like how many adepts a particular group can have, what the characters will be. Almost all of that will come out of, not all of it necessarily comes out of this relation, but much of the information will come out just from this relation. Okay, any further questions? I really shouldn't keep the organizers stay on for this long, but still.
No, this is quite useful. And I think if somebody has any other questions, then please come up fast.
Okay, sir. Can I ask a question?
You go ahead. Everybody can ask questions. You go ahead.
My question is actually about previous lecture. Once you said something about unitary representation and non-unitary representation, then you say that non-unitary representation can be equivalent to some finite dimensional.
Let me say I made a very specific statement there. For a finite group, every unitary representations are special kinds of representations, right?
Yes.
But if you have a finite group, then you can show each and every one of its representations is equivalent to a unitary representation. I didn't say every representation is unitary, but I said that you could do a similar transformation and go to a unitary representation. By the way,
in Lorentz transformation, I have finite dimensional transformation, but non-unitary.
Yeah, finite dimensional transformations. It's not a finite group, right?
No, yes, it's not finite group.
It's not a finite group. But by the way, this result that I stated actually extends to infinite groups as well. But for that, you need the infinite group to be compact. Why? Essentially because for compact groups, this kind of thing that I did, this summation, interchanging a summation. In fact, the proof of the unitary equivalence to the unitary representation that I had earlier, which I did not show you, essentially had a very similar technique to the one that I used right now. Summation over the entire group. And there what I did was, here also what I did was this. If you look at the proof, the key part of the proof of was this. Okay. This is what we started with, right? And the next step we said we can move the d alpha g inside the sum. That is, we can interchange the multiplication by the matrix and the summation. Of course, the summation becomes an integration when you go to an infinite group. And there, or at least when you go to a continuous group, not just an infinite group, but if you have a continuous group, the summation will essentially go over to an integration. And there the question will come, can I actually interchange this matrix multiplication or operator multiplication, as the case may be, with the integration? And the answer is you can do that only for compact groups. So the proof that I gave, or I did not give for that theorem, but the proof uses a trick very similar to this one. That proof will work only for compact groups. Now, what exactly are compact groups? The technical definition is a bit tricky, especially if you don't have a background in topology. But roughly speaking, a compact group is one for which the space is compact, is sort of closed and bounded.
Yes, yes.
Now, for the Lorentz group, the parameter space is V, and V can take, V is open, right? It cannot reach up to C.
Yes, rapidity.
Rapidity goes all the way to infinity.
Yes.
Right?
Yes.
Rotation group, on the other hand, has parameters, angles, which are bounded by 2 pi. Okay, I'm oversimplifying, but rotation group is compact, Lorentz group is not. Which is why rotation group actually has unitary representations, unitary finite dimensional representations. The Lorentz group actually has finite dimensional representations, plenty of them. In fact, the Lorentz transformations themselves form the defining representation, but they are not unitary.
Yes,
Lorentz group also has unitary representations.
You
can find unitary representations for the Lorentz group, but they are infinite dimension.
Yes.
You can't find finite dimensional unitary representations for the Lorentz group, because that proof that I talked about, that theorem works only for finite groups, can be extended to compact groups, cannot be extended to non-compact groups. In fact, I'm pretty sure that somebody is going to talk a lot about representations of the Lorentz group, because that's what I saw in the title. And this issue will also come up there, I guess.
Okay.
And this is a very important thing physically. The fact that Lorentz group does not have finite dimensional unitary representations, but only unitary representations in infinite dimensions is actually very important.
I studied that the unitary, for Lorentz group to be unitary representation, it should be infinite dimensional. So I was
yeah, but that's not a contradiction with this, because the condition for this does not apply there.
Yes, yes, yes.
The theorem that the proof which I skipped, but the proof which I had was only for finite groups, can be extended to compact, but cannot be extended to non-compact groups.
Okay. Thank you.
So the proof does not work. That does not mean the result will be false, but in that case the result is false. Just because the proof cannot be extended doesn't mean that the result will not work. But in this case the result does not work. That was a general statement. Just because the proof fails doesn't mean that the result necessarily fails.
Okay.
Okay, any further question?
Sir?
Yeah.
Yeah, sir, in the if a set of operators is said to be irreducible if there exists no common invariant subspace except for the trivial ones, right?
Yeah, right. Them. So there exists no non-trivial invariant subspace of the vector space V. Yeah.
Yeah. So my question is that so it's obvious that there would be no common eigenspaces between them. Because eigenspaces are obviously invariant. So is the converse true? Like if there are no common eigenspaces between the set of operators, then are they irreducible?
No.
Okay.
Because eigenspaces would mean you have to reduce them down to one-dimensional. Remember, an eigenspace essentially means that every vector essentially mixes with only itself, right?
Yeah.
What is an eigenvector? An eigenvector is one on which when a t acts, you get a multiple of it. So a vector only stays within its own subspace. So that will happen only if you broke down every one of the subspaces to one-dimensional subspaces.
Okay, and if I
that will happen for an abelian group, by the way.
Okay, and if I talk about the generalized eigenspaces, then
that's exactly what we will cover in the next couple of lectures.
Okay.
Because you will not be able to, the point is you will not necessarily be able to diagonalize every one of the D's. You will only get to block diagonalize them.
Yes.
So if you have a matrix which commutes with every one of them, and that's something which happens very often. For example, if you have a Hamiltonian for a quantum system and you have some symmetry operations, then the Hamiltonian commutes with every one of the symmetry operations.
Yes.
Okay. But does that mean that the Hamiltonian is going to be a multiple of the identity? The answer is no, unless your vector space is an irreducible vector space. That is, the representation is irrep. Typically, the physical representation that you will get very often will not be an irrep, but it can be built out of irreps. Okay. That is, if it's a reducible representation, you can reduce it into blocks. The question is, what do these blocks say, this block structure say, about the possibilities for the Hamiltonian or any operator which commutes or any matrix which commutes with all the group matrices. And it will turn out that it's not exactly trivial, but a huge amount of restriction comes from this and huge amount of simplification in the kind of work that we will actually have to do. So for example, in the square molecule, just by looking at the fact that the force matrix has to essentially commute with all the 8 D's, dA, dB, dC, dd, and so on, that will actually put severe restrictions on the force matrix. That will tell you that only certain kinds of vibrations are possible. And we can even figure out what the normal modes will look like, which normal modes will be degenerate, which ones will not be, and what the normal modes will look like, what kind of oscillations you will get. All this can come out by using group theory. Essentially, most of it will come out by using the Great Orthogonality Theorem in various versions.
Okay. Yeah.
Okay. Anything else?
Okay, so if there are no further questions, I think we can wrap it up for today. And I thank again Professor Dasgupta for giving such a fantastic talk. And let us meet again for his talk tomorrow.
Well, there's a talk before that also, I guess. My talk tomorrow is at 4.
4, yeah.
So everybody will meet at 2, I guess.
Yeah. Tomorrow, 2 o'clock, I think Sachinda Vaidya is going to talk again.
So you are going to talk about the Lorentz group, right?
Yeah. I'm going to. In fact, what I am finding is that you have covered most of the basic things which I would require. Actually, it will facilitate me my talk to a great extent.
Yeah, but I have not been able to cover whatever I wanted to, but I will just try to make it sort of understandable whatever I say.
No, it is very well done. Means it will give them a very good background actually. So I can actually go a bit faster during my presentation. And,
okay, hopefully that will be useful. Thank you.
Yeah.
Okay, I will just wrap it up today.
Wrap it up, okay. And so please be there at 2 o'clock tomorrow and for Sachin with this talk, and then it will be followed by Professor Dasgupta again at 4 o'clock, and then at 6 o'clock I think Professor Frederick Skoll will talk on dynamical symmetries, things like that. So please be there and try to maximize your number of presence should be more. Actually now I find this barely 25 or something.
So that's because people have been dropping out regularly.
But
that's understandable. It has been long.
Okay then.
Okay, anyways.
Good night to all of you.
Good night.